Simplex method is an approach to solving linear programming models by using slack variables and pivot tables as means of finding the optimal solution for optimization problem. Essentially, the problem is that of finding the particular vertex of the convex region which correspond to the optimal solution. The most commonly used method for locating the optimal vertex is the simplex method or simplex technique or simplex algorithm, which was developed by G. Dady in 1947. The simplex method provides an algorithm which consists in moving from one vertex in such a way that the value of the objective function all the succeeding vertex is more or less the case may be than the preceding ones. The procedure of jumping from one vertex to the another is then repeated. Many of the problem will be converted to LP and then solved via simplex method. Assuming the existence of an initial basic feasible solution, an optimal solution to any LPP by simplex method is found as follows. So first, standard form into the equation, converted it into the equation, determining the slack variables, setting up the table, check optimality, then identifying the table, then test for the feasibility, create new table and check optimality, then identifying the variables. So first step is to check whether the objective function is to be maximized or minimized. If it is to be minimized, then convert it into a problem of maximization, that is minimize z is equal to minus maximize. So for the maximization problems, if all zj minus cj is greater than or equal to 0, then the current basic feasible solution is optimal. If at least one zj minus cj is lesser than 0, then it is not an optimal solution. So here is an LPP problem that should be solved using simplex method. So maximize z is equal to 4x1 plus 10x2. Subjective constraints are 2x1 plus x2 is lesser than equal to 50, 2x1 plus 5x2 is lesser than equal to 100, 2x1 plus 3x2 is lesser than equal to 90. By introducing the slack variables s1, s2 and s3, problem in standard form. So that becomes maximize z is equal to 4x1 plus 10x2 plus 0s1 plus 0s2 plus 0s3. Since there are 3 equations with 5 variables, the initial basic feasible solution is optimized by equating and then 2 variables to 0. The initial basic feasible solution is s1 is equal to 50, s2 is equal to 100 and s3 is equal to 90. Non-basic, this initial iteration table. So here the net value is calculated, and then since there are some zj minus cj is lesser than 0, so the current basic feasible solution is not optimal for this maximization problem. Since it is minus 10, so the negative value, the most negative, the corresponding non-basic variable x2 enters the basic, and the column corresponding to the x2 is called as key column. The leaving variable is the basic variable s2, which corresponds to the minimum ratio, so that's 20. The leaving variable rho is called as key row, and the 5 is the key element. So now the new equation is equal to old equation divided by key element. By all the calculation, the improved basic feasible solution is following the first iteration table. So here, since all the zj minus cj is greater than or equal to 0, the current basic feasible solution is optimal. So for the maximization problem, zj minus cj should be greater than or equal to 0 to get the basic feasible solution as optimal. So, and then the optimal solution maximum is equal to 200. So that, and for there x1 is equal to 0 and x2 is equal to 20.